So, minimization of Boolean expression. So, there can be two methods that can be applied for doing this minimization. One method is known as algebraic minimization and other one is using a map based method which is known as Carnot map or K map in short. So, this algebraic method, so we have already seen some Boolean expression conversion using algebraic method that uses the Boolean identities for reducing the or converting one Boolean expression to another Boolean expression. And this Carnot map is another map based method which is much simpler compared to algebraic method. So, both of them can give us minimum form, but this algebraic method. So, there is no as hard and fast rule that you have to apply the algebraic manipulations in this order to get the minimum form. So, that makes it difficult, whereas in Carnot map. So, there are some rules, if you follow those rules then you will definitely get a minimum form expression. So, this algebraic method, the different Boolean rules and theorems that we have discussed in our previous classes. So, they can be applied for simplifying the Boolean expression in this method. So, this is the algebraic method. So, we will take some example, like say this is a this is a Boolean expression. So, this in fact in canonical sum of product form. So, if you want to simplify this, then this a b bar c bar and a b bar c. So, if you take a b bar common from these two terms, so you will get c bar plus c. So, c bar plus c is equal to 1. So, as a result these two terms if you combine them, so you will get like a b bar. Similarly, between these two terms, so if you take a b common, you will again get c bar plus c. So, that c bar plus c evaluates to 1. So, you get a b bar a b, and then between these two terms. So, if you take a common, so you will get b bar plus b, that is equal to 1. So, this will also get cancelled. So, you will get a. So, in this way we can convert this Boolean expression into a corresponding simplified form a bar b c plus a. Of course, there is no guarantee that if you are applying this Boolean rules, so there is no proof that this is the exact minimum form. Okay. In this particular example, that may be the case, but in general there is no such guarantee. Similarly, if we take say another example, so a b bar c d bar plus a b bar c d plus a b c d bar plus a b c d. So, here also if you take a b bar c common from the first two term, you will get like a b bar c into d bar plus d. So, d bar plus d is equal to 1. So, you get a b bar c. Similarly, between these two terms, so you take a b c common. So, it is d bar plus d. So, this that is equal to 1. So, after getting this, so if you take a c common from these two terms, so you will get b bar plus b. So, b bar plus b evaluates to 1. So, you get a c. So, in this form you can apply these Boolean identities to convert these Boolean expressions into some minimized form. Of course, as I said that it is not proved to be absolute minimum. Okay. So, we can do some exercise. This is say this x bar y bar z plus this thing. So, if you want to do this, so you can say, so between the first two terms, so you can say I can take x bar z bar common and inside is y bar plus y. Similarly, from the second two terms, so I can take x z bar common and I get y bar plus y. So, that boils down to x bar z bar plus x z bar, and again between these two terms. So, you can take z bar common. So, you can write it as x plus x bar into z bar. So, x plus x bar evaluates to 1. So, 1 into z bar, that is equal to z bar. So, that way you can do the simplification, and this one if you want to simplify, then a in. So, you can do many things, like you can say that I will take so this b is there. So, this b bar c plus b bar c bar. So, you can take b bar common. So, you get inside as c bar c plus c bar, and then this c plus c bar is equal to 1. So, a into b plus b bar into 1, that is a into b plus b bar. So, b plus b bar is again equal to 1. So, you get a. So, this way you can simplify the Boolean expression. So, you can try to verify these rules. So, this x plus y plus z into x bar plus y plus z equal to y plus z. So, How to do this? So, you can convert them, you can do a straightforward multiplication, like say if you multiply, so you will get like x bar plus x y plus x z plus y x bar y plus x bar z plus so x bar y plus so I have taken x bar plus x y plus x z plus x bar y bar is 0. Okay, let us write in a proper form, otherwise this will be difficult. So, we have got so this y, now I am multiplying by y. So, y x bar is x bar y plus y. So, that is equal to y is y plus y z, okay, plus then this z into x bar. So, this is x bar z plus this z y z plus z. So, x bar is 0. So, this cancels out. So, we have got x y plus x z plus x bar y. So, this y plus y z. So, this is basically if you take y common. So, it is 1 plus z. Similar, then this is x bar z plus, again if I take z common. So, it is y plus 1 into z. So, this is x y plus. So, if you take these two terms together, this x y and this x bar y. So, this is x plus x bar into y plus, again if you take this x z and x bar z together. So, you get x plus x bar into z plus this now this y into 1 plus z. So, the 1 plus z is equal to 1. So, get a y here, and this 1 plus y equal to 1. So, get a z here. So, this is y plus z plus y plus z, that is equal to y plus z. So, this way you can verify this. Okay. So, this is proved. So, we can use Boolean identities for getting this thing. Similarly, a plus a bar b bar. Okay. So, what you can do? So, you can just convert it into so b plus b bar plus a bar b bar. So, you get like a b plus a b bar plus a bar b bar. So, you get like, so this is a b plus a b plus b bar. So, a b plus b bar. So, if you so a b plus b bar. So, then from there you can reach this a plus b bar. Actually, this b bar, it can be written as so it is you can show it or you can start from the other side, like at this point you can just a b plus b bar plus you can take these terms twice. So, a b plus a b bar, so a b plus a b, like that, and then you can do some simplifications to come to this form, or you can take a truth table and then show that this a plus a bar b bar is equal to a plus b bar. So, next we will see this Carnot map method. So, this Carnot map or K map. So, this was invented by Maurice Carnot in 1953. So, this is the refinement of Veit's 1952 Veit diagram, which is a method to simplify Boolean algebra expressions. So, K maps, so they are a very convenient way to express Boolean expressions. They can be used for up to 4 or 5 variables. So, in some cases you can expand to 6 variables as well. and they are visual representation of a truth table. So we will see how they look like. So, this Venn diagram, so this we are all familiar with Venn diagram. So, that is for set you can represent it. So, this is the universe, and suppose I have got A and B as two variables, or they are representing two sets. So, there may be intersections and some portions may be common. Now, outside this region of these two sets, so I have got the region which is represented as A bar B bar. Similarly, this part which is common between A and B, so that we represent as A B, as if both of them are there, both of them are true. This part A is there, B is not there, so it is A B bar, and this part A is not there and B is there, so it is A bar B. So, you can also tell, if you write down the corresponding index, like A bar B bar, the index value is 0, A B bar index value is 2, A B index value is 3, and A bar B index value is 1. So, this way I can write down the mean term expressions like M 0, M 1, M 2 and M 3. So, this can be represented in the form of a rectangular region which is divided into 2 in each side, since I am considering only 2 sets or say 2 variables. So, I can represent it as one this part, this side I represent A and this side I represent B. So, when I am on this part, so this is both A and B are equal to 0. Here A is equal to 0, but B is equal to 1. So, this is A equal to 1 and B equal to 0, and here both of them are equal to 1. So, I can represent it like this. So, for the sake of simplicity, I can just drop these terms M and I can write it as 0, 2, 1, 3. So, this is also this A B. So, this is one form in which I am writing it. So, you can also this is also a standard representation where we put a diagonal line here, and this side we write A, this side we write B, and then we write like 0 plus this A equal to 0 and 1, B equal to 0 and 1. So, this is 0 1 0 1. So, like that. So, you can say like say this is my full so this is another way of representation, like say this one. So, first term, so this is 0 0. So, whatever be the value of the function, so we can write here. Okay. So, this is, if this value is say, if this value is say 1, so this is 0, this is 1 and this is 0. So, we will what we will do, so at this place we will write a 1, then this 0 1, so we will write a 0 there, then 1 0. So, this will write as a 1 here, and 1 1 will write a 0 there. So, this way we can fill up this table. Okay. So, this is known as the Carnot map for a function. So, this is a Boolean function, and we can make the corresponding Carnot map like this. So, this helps in representing the functions. Like now, what happens to the 3 variables? So, if I have got 3 variables, so in the Venn diagram notation we have got A, B and C as 3 circles, and there if you see that overlapping. So, this part is here all the 3 sets are present. So, it is A, B, C. Okay. So, outside is A bar, B bar, C bar. So, here I have got A bar, B bar, C. Okay. So, because the A and B are not there, only C is there. So, this way for every region you can figure out the corresponding part of the set which is present there. And now, in the same fashion, so we convert it into this mean terms. So, outside is M 0. So, this is M 1, then this is M 2. So, like that we can write down the corresponding mean terms. So, in a tabular notation, so A and B, they are put on the row side, and C is put on the column side. So, 2 variables will be put on the row side and 1 variable will be taken at the column side. So, that way, so this A B is 0 0, 0 1, 1 1 and 1 0. So, you note you take the notation that this A is represented by these 2 rows, these 2 columns, and B is B equal to 1 spans over these 2 columns. So, A equal to 1 spans over these 2 columns, B equal to 1 spans over these 2 columns, C equal to 1 spans over this particular row. So, this part, this particular column, A and B both are 0, and here A is 0, B is 1. Okay. So, that way we can have different rows and columns representing different parts of the this diagram, and ultimately we have got this rectangular box, where you can, this is also a notation, standard notation, that is we write A B here and C here. on this side we enumerate the combinations 0 0, 0 1, 1 1, 1 0. This side we enumerate the combination for C 0 and 1. Now, given the function, so we will populate these entries and accordingly we can fill it up. So, 4 variables. So, if you are taking 4 variables, then this A B, so we were using the row side for representing 2 variables. Now, we will be using the column side also for representing 2 variables, A B and C D. So, 0 0 0 1 1 1 1 0 and C D 0 0 0 1 1 1 1 0. And so, in a sometimes we write it in this format also, that for these 2 columns A is 1, for these 2 columns B is 1. So, like that is also a standard notation. So, generally we will be using this notation for most of the cases, but sometimes we will be going to this notation as well. So, for 5 variable what we do, we take 2 maps. Okay. So, in one of the map A is equal to 0. So, you see all the combinations that we have here, A is equal to 0. Okay. So, this is 0. So, here also A is 0, here also A is 0, and on this side I have taken all the maps where A, all the permutations where all the combinations where A is equal to 1. So, that way we, as if we split the map into 2, one for A equal to 0, other for A equal to 1. So, this way we can go for 5 variable maps. Okay. So, though they are not a single map, but we can go for in this way, or you can also visualize it as if this is a 3D. So, one is stacked over the other. So, here it was a 2D, up to 4 variable the map remains 2D, but when you go to 5 variables, so map becomes 3D. So, you have to expand in another direction on the vertical direction. 6 variable. So, again, so as you can understand that I have to have 4 maps. Okay. So, for this map A equal to 0 and B equal to 0, for this map A equal to 0, B equal to 1, here A equal to 1, B equal to 0, and for this map I have got A equal to 1 and B equal to 1. So, this way the min terms get distributed over the number of maps, okay, number of tables, and then we can try to do some manipulation with those numbers and get the minimized form. And similarly, so this is also another notation of the same map, the 6 variable map. Now, how the truth table gets represented in the form of a Carnot map. Okay. So, 2 variable, suppose this is the function. So, A B 0 0 0 1 1 0 and 1 1, for 0 0 0 1 and 1 1, the value of the variable, value of the function is 1, otherwise it is 0. So, in the Carnot map, so we represent the min terms by putting a 1 at the corresponding location of the Carnot map. So, so these 3 1s were there. So, these 3 1s we have put here. Okay. So, this is the representation of this truth table in the form of Carnot map. So, min terms are represented by a 1 in the corresponding location in the Carnot map. So, 2 variable Carnot map. So, it is adjacent ones can be paired off. So, we can do it like this. So, this is 1 and this is 1. So, these 2 can be paired together and we can get a pairing of them. So, this is so in this, so the term that we have is, so if you look into this, so it is A bar B bar plus A bar B. So, here it is A bar B bar plus A bar B. So, if I do a simplification, so A bar B bar plus A bar B. So, here if I take A bar out, so I will get B bar plus B. So, this B bar plus B is equal to 1. So, this simplifies to A bar. So, that means, if I have got 1s at 2 successive places and I do circle them, combine them together, then one of the variables get eliminated. So, in this case B is changing from 0 to 1. So, whichever variable change its polarity, so that variable gets eliminated. So, this is the variable B has got eliminated. Similarly, if you look into this term, then what is happening is, so this is nothing but A bar B plus A B. So, in a similar form, so you can say take this B common, A bar plus A into B, and A bar plus A equal to 1. So, you get a B here. So, here this the term A has got eliminated. So, in this way, once we have represented the function in Carnot map, So, we automatically do this type of grouping and eliminate variables for getting the minimum form. So, this is the beauty of Carnot map. So, once you have drawn it, so you can just go on grouping them and getting the minimum form, and there is a proof that these are going to be the minimum one. So, there are certain rules. So, if you follow that, so there is a proof that you will be definitely getting a minimum sum of product form. Let us take a 3 variable function. So, this ABC, the combination varying from 0 0 0 to 1 1 1, and this is the output column, the function P. Now, in a so this is 1 at 0 1 0, 1 0 0 and 1 1 0. So, this is 0 1 0. So, 0 1 0 is this one, then we have got 1 0 0. So, 1 0 0 is this one and 1 1 0 is that one. So, in this, if you see that I can this is the representation, and then I have to I can do a I can do something called this grouping, as we were doing in the previous example. So, one square is filled in for each min term, and here you see one thing, that the way we are writing these indices. So, this is 0 0 0 1 1 1 and 1 0. So, it is, you just keep in mind that it is not like 0 0 0 1 1 0 1 1. So, it is not the binary ascending order, but it is in some sort of gray code. Okay. So, this you will see later that this is something called this type of coding where only one bit changes between successive terms. So, that is called a gray code. So, it is 0 0 to 0 1, only the LSB is changing. Similarly, 0 1 to 1 1, only the second bit is changing, and 1 1 to 1 0, again only the LSB is changing. So, when only one bit is changing, so we get a gray code. So, this gray coded form, so this is useful because when you are grouping, so if I have got two successive terms, so if you write here, so instead of this row being this column being 1 1, so if this was say 1 0, then if you are trying to combine these two, then the problem is that the more than one variable is changing, but in that case it will be a wrong one. So, we cannot take more than one variable changing between the successive terms. So, that is that is the rule of this Carnot map. So, you have to take it in the gray coded format. Now, the grouping part. Okay. So, this first the example that we have. So, for that, so you can do a grouping like this. So, where I have got ones at two successive places in the vertical direction, and the term that gets eliminated is given by. So, this is this can be written as say this is A bar. So, A bar sorry, this is basically A bar B C bar plus A B C bar. Okay. So, this one is A B C bar and this one is A bar B C bar. Now, if you combine them, so this is this B C bar is common between them. So, you get A bar plus A into B C bar. So, this A bar plus A equal to 1. So, you will get B C bar here. Also, while you can think this Carnot map to be some sort of folded one. So, this last row or the last column, you can take it as if the whole table has been folded. So, you get this last column adjacent to the first column. Similarly, if you have got more size, the higher sized Carnot map, say 4 by 4 Carnot map, then also you can take this folding. So, you can take as if this part is at this row is adjacent to this row, and again this column is adjacent to this column, because it is folded in the both in the row wise and the column wise direction. Because of very simple reason, like if you look into these two patterns, so this is 0 0 and this is 1 0. So, only one bit is changing between them. So, whenever only one bit is changing, the columns are considered to be adjacent. Similarly, between the rows, if only one bit is changing, so we will consider the rows to be adjacent. So, here by following that rule, so this 0 0 and 1 0, so these two columns are adjacent to each other. So, we can do a grouping taking the corresponding ones. So, if you do that, then you will be getting like so this is so this term is A B bar C bar, and this term is A B C bar. So, if we do that, so if we take this a c bar common, so you will get b bar plus b. So, b bar plus b is equal to 1. So, you get a c bar. So, ultimately, so we have got this a c bar term from the from this blue square, and we have got this b bar c term from the b c bar term from the first one. So, the overall function is so this is that's what I was telling, that it is a wraparound connection. So, wraparound, so we can wrap around, and we can say that we can get more number of minimizations for this part. Okay. So, next we will see another example. Suppose we have got an expression like say a b c plus a b c bar plus a bar b c plus a b c bar. So, in the index notation, so this is basically, so this is 7, okay. Then this is a b c bar, so that is 6. Then we have got a bar b c, that is 3, and a b c bar is, so a b c bar is written twice, okay. So, there is something wrong here in the example. So, this is a bar b c plus a bar b c bar. So, this should be a bar b c bar, this is not a b c bar, so a bar b c bar. So, a bar b c bar is 2, okay. So, these are the 4 terms in index notation. So, we have got 4 terms like this. Now, so this is the function. So, we have got if you look into the corresponding Carnot map, so it is a 3 variable map, and we will have situation like this. So, this this a bar b c bar, so a bar, so it will be on this row, b c bar, so this one, so this is 1, then 0 1 1, so a bar b c, so a bar b c, so this is also equal to 1. Then we have got a b c bar, so a b c bar, so this this one, so this is 1, and then we have got a b c, so this is 1. So, ultimately what you get is a 4 ones which are close to each other. So, they are all one hop away from each other. So, you can see that this expression, so you can, whenever you have got more than 4 ones, so you can club them together into a group of 4 ones, and then if you do a minimization by using Boolean identities, then you see that this whole term it reduces to b. So, in terms of Carnot map, you can, what you can say in this case, you see A is changing its polarity from 0 to 1. If you consider these 4 terms, A is changing its polarity, and your C is also changing its polarity. So, it is becoming 1 to 0. So, what is not changing is the polarity of B. So, this whole quad, so it can be written as the term, the variable which is not changing its polarity, that is B. So, without doing this this algebraic manipulations, so we can directly write that the term corresponding to this quad will be B. So, you just note down the variables which are not changing its polarity.